winds of 200 kilometers per hour, earthquakes that make the ground move like water, gravity pulling on structures weighing hundreds of thousands of tons. These are the invisible enemies every engineer faces before placing a single stone on the ground. But some buildings don't just survive these forces, they master them. They turn them into solutions so elegant they look like magic. Today you will discover the 10 constructions that most challenge what physics should allow. This is not a ranking of beauty. It is not a ranking of height. It is a ranking of engineering solutions that redefined what is possible to build on this planet. In March 2011, Japan was struck by the largest earthquake in its recorded history, magnitude 9.0. The ground in Sendai swayed for minutes, buildings collapsed, and the Sendai Mediatek remained standing, virtually intact. The reason lies in the most radical idea of architect Toyo Ito, eliminating conventional walls and columns. Instead, he used 13 tubular steel tubes with diameters ranging from 1 to 9 meters, running through the building from floor to ceiling in a helical form, resembling steel trees growing from the ground. These tubes are not decorative, they are the entire structure of the building. The helical geometry causes seismic forces to be distributed in a spiral along the tubes, dissipating energy instead of concentrating it at a single breaking point. It is the same principle as a spring. When it twists, it absorbs impact without breaking. When the 2011 earthquake struck, strong enough to shift the Earth's axis, the Mediatek swayed, but the structure responded exactly as it was designed to, flexible where it needed to be, rigid where necessary. A monument to engineering that literally saved the building itself. In Shanghai, a tower seems to twist against the wind itself. It is not an optical illusion, it is engineering pushed to the limit. The Shanghai Tower is the second tallest building in the world, standing at 632 meters. But what truly makes it extraordinary is not its height. It is the way it was designed to confront one of nature's most unpredictable forces, the wind. Instead of rising straight like a rigid block, the tower rotates 120 degrees along its height. This twist reduces wind pressure on the structure by about 24%. Less resistance means less structural stress, less material, and greater efficiency. It is physics applied with surgical precision. Shanghai is hit by seasonal typhoons and intense gusts. In traditional skyscrapers, this creates uncomfortable vibrations and extreme loads on the foundation. Here, the solution was twofold: external aerodynamics and internal control. At the top, a tuned mass damper, weighing hundreds of tons, acts as a counterweight, reducing oscillations to levels almost imperceptible to those inside. But the innovation does not stop at wind resistance. The tower features a double-glass facade system that creates 9 internal vertical zones. These atriums function as natural thermal buffers, reducing energy consumption and improving climate efficiency. It is a skyscraper that not only challenges physics, but also optimizes every interaction with its environment. Its foundation extends deep into the region's soft soil, supported by hundreds of structural piles. Everything was calculated to absorb massive loads without compromising stability. The Shanghai Tower is not merely a symbol of height. It represents a new generation of megastructures, buildings that do not fight against the forces of nature, but learn to work with them. When you look at this spiral of glass cutting through the sky, you are not just seeing a building. You are seeing mathematics, wind, and gravity working together, at the edge of what is possible. Chicago is called the Windy City for a reason. The air currents that funnel between its skyscrapers can be brutal. And for tall buildings, wind is not just a discomfort for residents. It is a real structural force that can cause oscillations, material fatigue, and, in extreme cases, structural failure. The Aqua Tower, with its 82 stories, looks sculptural. Its balconies vary in size and shape on every floor, creating that wave-like appearance reminiscent of moving water. But architect Zhang Gang did not design those balconies for aesthetics alone, or at least not only for that. Balconies with different shapes on each floor disrupt the formation of wind vortices. In conventional buildings, wind creates pressure pockets that synchronize and begin pushing the structure rhythmically. The same phenomenon that brought down the Tacoma Bridge in 1940. The Aqua Tower's balconies interrupt that rhythm. Each floor speaks to the wind differently from the one below. The result? Up to a 30% reduction in the wind forces the building must withstand. Less structural load, less material, lower cost. Beauty transformed into engineering. In the heart of Tokyo, among neon lights and train tracks that never stop, rises a tower that seems alive. It has no dominant straight lines or aggressive angles. Its oval shape, wrapped in an interwoven white mesh, resembles a cocoon about to open. The Mode Gakuen Cocoon Tower was not designed merely to impress, it was created to survive. Standing at about 204 meters tall, it houses 3 educational institutions in one of the most seismically challenging environments on the planet. In Tokyo, building high means facing frequent and unpredictable earthquakes. Unlike many skyscrapers that rely solely on extreme rigidity, this tower embraces controlled flexibility. Its structure uses a reinforced central core system, combined with an external diagonal mesh that distributes lateral forces. When the ground moves, the building does not try to resist rigidly. It absorbs, dissipates, and redistributes energy. The oval shape is not just aesthetic. It reduces stress concentration points and improves aerodynamic performance, decreasing wind-induced vibrations. The diamond pattern facade acts as a structural exoskeleton, reinforcing the whole structure like armor integrated into the building's body. Inside, the floors are organized around a vertical core that concentrates circulation and stability. Every detail was calculated to maintain a balance between visual lightness and structural strength. On the skyline of New York, there is a structure that represents more than height. It represents resilience. A building born from a void and designed to become one of the safest ever constructed. One World Trade Center rises to 541 meters, a number that is not random, 1,776 feet, a direct reference to the year of the United States independence. But beyond symbolism, it is a landmark of extreme structural engineering. Its base is formed by a massive reinforced concrete core with thick walls capable of withstanding severe impacts. Unlike many skyscrapers that prioritize lightness, here the priority was resilience. The building was designed to resist hurricane-force winds exceeding 200 kilometers per hour, explosions, and extraordinary structural loads. As it rises, its geometry transforms. The square base gradually rotates to form an octagon, creating a faceted silhouette that reduces wind pressure. This twist is not merely aesthetic, it redistributes forces and improves aerodynamic performance, reducing oscillations at the top. Inside, redundant systems ensure rapid evacuation and enhanced safety. Wider staircases, protected cores, and fire-resistant materials are part of a design conceived down to the smallest detail. One World Trade Center was not built merely to be tall, it was built to be strong, to face wind, gravity, and external threats with a level of preparation that redefines global standards. It dominates the Manhattan skyline, but its true greatness is invisible. In the structural calculations, in the reinforced concrete, and in the engineering that transformed memory into permanence. Have you ever heard of the Leaning Tower of Pisa? Tilted 3.99 degrees after centuries of soil subsidence. A historical anomaly that became a tourist attraction precisely because the tilt was an accident. Capitol Gate in Abu Dhabi was built with an 18-degree deliberate lean, 4 times more than Pisa, and tilted on purpose. The structural challenge is colossal. A leaning building experiences forces that a vertical building simply does not. The center of gravity is displaced from the center of the base, which means the structure is constantly trying to tip over. In a 160-meter, 35-story building, that tendency toward collapse is enormous. The solution was a diagonal steel mesh on the building's facade, 12,500 interconnected steel elements that redistribute the weight to the foundation columns so that no single point receives excessive load. The mesh functions like an external armor that keeps the structure in constant balance, and the foundations, 490 concrete piles, some reaching 30 meters deep, some pre-tensioned to create tensile resistance. Because in a leaning building, part of the foundation is literally pulled upward by the weight on the opposite side. Guinness Records certified it as the world's furthest intentionally leaning habitable building. There is a specific point in Beijing where, depending on the angle, the CCTV headquarters appears physically impossible. Two skyscrapers rise from the ground, lean toward each other at the top, and connect in a horizontal structure suspended in the air, a closed loop, a giant ring of concrete and steel. Architect Rem Koolhaas said he wanted to create a building that was a section of the city suspended in the air. A beautiful concept. An engineering nightmare. A conventional building transfers loads vertically, from the roof to the ground, always downward, always predictable. The CCTV headquarters creates forces that move in completely opposite directions at the same time. The cantilevered section at the top, 75 meters projecting horizontally into the air, creates tension on one face of the structure and compression on the opposite face simultaneously. The two leaning towers multiply the complexity. To calculate the load flows in this structure, Arup engineers needed structural analysis software normally used for aerospace projects, not buildings. The computational model contained more than 70,000 individual structural elements. And there was still the earthquake issue. Beijing lies in a moderate seismic zone. A looped structure is particularly vulnerable to earthquakes because seismic forces travel around the ring and amplify rather than dissipate. The solution was to make the entire steel lattice of the facade part of the structural system. 56,000 tons of steel, distributed in patterns that appear random, but were calculated with millimetric precision for each segment of the structure. When the Sichuan earthquake struck China in 2008, during construction, engineers were on maximum alert. The building held, the mathematics worked. Taiwan is one of the most hostile places on the planet to build a skyscraper. It sits on the so-called Pacific Ring of Fire. Earthquakes are frequent, and every summer typhoons with winds exceeding 200 kilometers per hour sweep across the island. Building Asia's tallest tower here in 2004 required an engineering solution that did not previously exist. On the 87th to 92nd floors of Taipei 101, suspended by steel cables, hangs a golden steel sphere measuring 5.5 meters in diameter and weighing 660 tons. It is the world's largest tuned mass damper visible to the public, and it is literally a giant pendulum designed to save the building. The principle is elegant. When the wind pushes the top of the building to the right, the sphere, by inertia, tends to remain behind, to the left. That opposite movement cancels part of the building's oscillations. It is basic pendulum physics applied on a monumental scale. 8 hydraulic dampers connected to the sphere adjust its speed. Sensors distributed throughout the building feed computers that monitor the system in real time, 24 hours a day. In 2015, a Category 3 typhoon passed directly over Taipei. Winds reached 190 kilometers per hour. Taipei 101 swayed, exactly as it was designed to sway, and the golden sphere moved 100 centimeters relative to the building, absorbing energy that would otherwise have stressed the structure. No structural damage, no evacuation. The pendulum worked. The Tokyo Skytree is not only the tallest communication tower in the world at 634 meters. It is a testament to how modern technology can learn from ancient wisdom. Tokyo sits on one of the most active seismic fault systems on the planet. Engineers knew that designing a 634-meter tower in that location would eventually face a real test. The solution they found came from an unexpected source: the 5-story pagoda of Toji Temple in Kyoto, which is more than 1,200 years old and has never collapsed in an earthquake. The secret of the pagoda is that its central core, a wooden mast running the full height of the structure, is not rigid. It is connected to the floors by elements that allow the mast and the outer structure to move independently from one another. When an earthquake shakes the outer structure, the central mast responds at a different frequency, and the two movements tend to cancel each other out. The Tokyo Skytree applies the same principle but in concrete and steel. Its structure is divided into two independent systems: a central concrete shaft that rises like a solid cylinder, and an external steel tripod-shaped frame that supports the facade. The two systems are connected by special dampers that allow each to move slightly independently. And this controlled independence is what prevents vibrations from amplifying. In simulations using data from the 2011 earthquake, which shook Tokyo with a magnitude of 7.0, even though the epicenter was hundreds of kilometers away, the Skytree responded exactly as designed. The top swayed more than 2 meters, but structural stresses remained within safety limits. 1,200 years of Japanese wisdom confirmed in 37 seconds of shaking. "828 meters, the tallest building ever constructed by humanity, a third of a kilometer taller than the second place." To put it into perspective, you could stack 2 Empire State Buildings inside the Burj Khalifa and still have space left over. But the issue is not the height. The question is, how do you support something that tall without it collapsing, without it swaying dangerously in the wind, without it sinking into the hot, unstable desert soil? The answer begins with a shape. If you look at the Burj Khalifa from above, you will see a Y-shaped floor plan, 3 petals extending from a central hexagonal core. That shape is not a whim. It is the solution to the most serious problem engineers faced: the wind. In Dubai, high-altitude winds can exceed 150 kilometers per hour. In a conventional 828-meter building, those wind loads would be so intense that the structure would need to be grotesquely overdesigned, too expensive, too heavy. The Y-shaped plan confuses the wind. Each petal deflects airflow away from the others, preventing pressures from synchronizing and amplifying. Wind tunnel tests confirmed it. The shape reduces wind forces by up to 40% compared to a conventional tower of the same height. But wind is only the beginning. Dubai's soil is sand and sedimentary rock, not the ideal solid substrate for a 500,000-ton building. Engineers drove 192 concrete piles down to 50 meters deep, topped with a 3.7-meter thick foundation slab. 110,000 cubic meters of concrete were pumped into the foundations, more than in many dams. And the heat? Dubai can reach 50 degrees Celsius. Conventional concrete does not perform well at those temperatures. It weakens and reacts poorly with moisture from the nearby sea. Engineers developed a special concrete mix with fly ash and blast furnace slag that resists heat, salt, and time. And to prevent the sun from overheating the concrete while it cured, pours at the highest levels were carried out at midnight. 828 meters of engineering, a new solution for every problem physics presented. The tallest structure humanity has ever built. And every centimeter of it is an answer to a question that once seemed to have no answer. What these 10 constructions have in common is not height, cost, or fame. It is that each of them, at some point in the creation process, required someone to look at a problem that had never been solved before and find a new answer. Modern engineering is not the art of working within the limits of physics. It is the art of discovering that those limits are farther than we thought, and then going a little beyond them. The question is not, what will be the next building to challenge physics? The question is, what will we need to invent to build it?